Hello friends, welcome back to the continuation session of ACE online preparation and our ACE preparation league season 2, and this is our second session, right, in digital logic design. And today I have selected one small topic, one small subtopic, that is counters. First I will give you some brief idea about counters, and then I will start the session with one small module or subtopic of the main and very important topic in digital electronics, that is counters. Yeah, what is actually this is a topic I selected, see, asynchronous counter, but it is a subtopic of a counter. What is a counter? Yeah, it is a sequential circuit. Yeah, it is actually a sequential circuit consisting of n number of flip-flops, and they are having their own interconnections, such that we are arranging the flip-flops to get certain combination of binary, and the binary is nothing but it is a binary equivalent of number of clocks given to the counter. That is actually the thing we can see on the counter. I can say the counter is storing that number, and I can say the counter is displaying that number if you connect the display unit, and I can also say that the counter is counting the number of clock pulses given by the clock generator. So that is the reason we can use the counters. We can find the counters in various applications where you need frequency division. If you want to divide a frequency, we can use a counter. If you want to count certain number of clock pulses, and after completion of counting of certain number of clock pulses, if you want to enable some activity, yes, accordingly we can design the circuit. So in that project or in that types of circuits also, the counters can help us. And the counter is a key point for all FSM, finite state machines, because here we can learn some fundamental. I don't say counter is FSM, but here we can learn some fundamentals, same fundamentals and almost same things we can use in the next level sequential circuit design. And the top level sequential circuit design is actually FSM, finite state machine, and the basic level study of sequential circuit, if you ask me, I can tell you flip-flops. But I have decided that I would like to start actually now counters, asynchronous counter. That is actually the topic I have decided based on the students' comments from the last year. I mean session 1 of season 1. In season 1, so many students requested give the information about the counters. So even though it is little bit tough to understand, I will definitely made it very easy, because I have selected very simple topic within 45 to 60 minutes. I cannot cover the entire concept. We should understand that. Okay. So I will try my best to give you the maximum information, and I will just give you the related problems also. Not only the explanation, I shall let you know some of the related problems from the basic level. Just a single line of information, how many model questions, how many number of questions we can find in the GATE and ESE. That I will definitely let you know. Okay, right. And see, the counter is actually, this is what I have given the statement. It is just simply interconnected of the n number of flip-flops, such that the combined states at any instant of time will give you the binary equivalent of number of pulses or clock pulses. You can say pulses or clock pulses which are giving externally to the counter occurred up to that time. At time t equals to t0, we have started giving the clock pulse to a system. At a time t equals to t1, n number of clock pulses has been completed, and the counter will give you that count value in the display unit. Yes, and as I told you, counter is also used as frequency divider. We are using it for dividing the frequency, hence we can also call it as frequency divider. But by what value it is going to divide the frequency is actually decided by its modulus number. In this session, I will give you only a synchronous counter, how to find its modulus number and different modulus number based counter design in a synchronous mode and related questions, very simple task. Yeah, and counters are basically classified into two types. It depends on how we are providing the clock to the counter. See, finally, this is a counter, it is using to count the clock pulses, that is a basic line, okay, but you should understand that how many types of counters are available. If you see the broad classification of counters, we can find only two types, synchronous counters and asynchronous counters. So it is decided by how you are providing the clock to the counter. How you are providing the clock to the counter will decides the type of counter. It can be like synchronous counter or it may be asynchronous counter. The name itself, it is saying some information if you understand it carefully. Synchronous counter, it says that in synchronous counter, we are providing clock pulse to all the flip-flops simultaneously. So each and every flip-flop can clock simultaneously in case of synchronous counters. Whereas in asynchronous counters, we are not going to provide the clock to each and every flip-flop. We are going to provide the clock to the first flip-flop only, and the first flip-flop is used to drive the second flip-flop as a clock. That means every flip-flop is waiting for the clock excitation from the output of its previous flip-flop. So that here delay will be more, because in synchronous case at a time we are giving the signal, in asynchronous it is not like that. Every flip-flop has to wait for some triggering or clock signal from its previous flip-flop. So we can say the bottom line of the story of this particular thing is, compared to asynchronous counters, synchronous counters are fastest counters, right? Of course, there are some subtopics in asynchronous counters and synchronous counters. Okay, let me show you that. See guys, this is a basic definition I have given. In synchronous counters, all the flip-flops can clocked simultaneously. Just it is, don't worry what kind of flip-flop it is. Don't worry about it. It is a flip-flop having input lines. Let us assume JK, T, D, whatever. See, but this is a clock. You see, in case of synchronous counters, we are providing the clock simultaneously. It may be JK or maybe D flip-flop. It is decided by actual name of the circuit or name of the counter, right? In case of synchronous, we have some subclassifications. Of course, there are so many. Strictly speaking, the standard classifications are 4: ring counter, Johnson counter, series counter and parallel counter. Okay. And here, as there is no connection between output of flip-flop to clock input, so the second flip-flop is not waiting for the output of first flip-flop. So that based on the available data and clock excitation, it can take its own decision simultaneously. Each and every flip-flop can take the decision simultaneously. So that if you consider only the flip-flops in the counter, I can say if I give the trigger within the TPD units of time, every flip-flop will update its output within TPD units of time delay. TPD means propagation delay of each flip-flop. TPD stands for propagation delay of each flip-flop. That's it. As flip-flops are having same propagation delay, just by assuming that flip-flops are having same propagation delay, and once if you give the trigger simultaneously within TPD units of time, output will be ready. But in asynchronous counters, it is not like that. We are going to provide the clock to the first flip-flop. Let us say it is first and it is second flip-flop in the counter. So assume it is JK 1 and 1. Sir, why I should connect 1? I will let you know. But output of first flip-flop is acting as clock for the second flip-flop, so that the output of first flip-flop is driving the second flip-flop and so on and so on. So that every time, even though the clock has been given by the user or clock generator, second flip-flop has to wait for the output of first flip-flop. First flip-flop will take some time to update its output. After that, it will feel the trigger. Then once if the second flip-flop get the trigger and it will start its operation, again it will take some time delay. So from this basic idea, I can tell you some few important points about the design. As I told you, I am going to do some analysis and going to give you some important simple and basic level questions from the asynchronous counter. It may be asynchronous counter or maybe synchronous counter. It can be asynchronous counter or maybe a synchronous counter. See, there are some standard steps. There are some standard steps to understand the entire topic. First one, circuit operation. We should understand the circuit operation. I mean standard circuit operation. There are some standard circuits. The last one is a design. If you want to design your own counter, yes, it is possible, but it takes more time. After completion of the total analysis, the last one will be the design process. Okay, right. As I am talking about asynchronous counter, of course the steps are same in synchronous and asynchronous. So you need to understand the circuit operation properly, and after that we need to find some important specifications of the circuit, some properties of the counter. In that, there are so many, among all the important and very important one is modulus number. I will write it as mod number during the explanation. So what is a modulus number? I will let you know. It is simply the number of states of a counter in its sequence. Counter is producing the sequence. How many number of states are producing by the counter in that sequence is actually called as modulus number. It will play vital role. It will play, modulus number will play vital role in the entire counters part. I said entire counters part. It means in both synchronous as well as asynchronous. So that you should understand the detailed information and meaning of modulus number in spite of the counter, maybe synchronous or asynchronous, and you should understand how it would help us while solving the problematic part. Okay. And number of flip-flops required to design a particular counter or mod 10 counter or mod n counter. Number of flip-flops requires. Number of flip-flops requires. And delay based analysis. Strictly speaking, propagation delay. Propagation delay based analysis. And then you can understand what should be the minimum value of clock duration. We are providing clock to the counter. It cannot accept any clock period. It is having some limitations that you should know by doing the analysis with respect to the propagation delay. And then it will gives the maximum operating frequency of the counter. These relations are very, very important actually as per the gate. But today in this particular session, I think I can cover at least in asynchronous case, asynchronous counters case, I can cover at least up to these 3 points of certain standard circuits, right? And the counters are classified into, just now I told you, 2 types, asynchronous and synchronous counters. The synchronous counters are again having some subclassification like ring counter, Johnson counter, series and parallel counter. And after that we can go for our own design. It is a special, we are going to design, or in the actually in classroom course, or maybe at the time of preparation, you will get one extra topic. Of course, that is a main and typical topic. Yes, we need to design our own counter. I am giving the clock pulses. I am expecting the count sequence like this. I am expecting decimal equivalent of count sequence of certain counter like this: 0, 3, 5, 0, 3, 5 like that. Initially it should be 0. After 1 clock I am expecting 3. After second clock I am expecting 5. Sir, is it possible? Yes, it is possible. We can design the sequence. Based on that, 2 questions are given already in gate for 2 marks. But that is under synchronous case. I am sorry, it is under synchronous counters case. Coming to the asynchronous counters, there are actually 2 types, up counter and down counter. Even though you can find down counter circuits in the problems, but I will talk about some common properties of up and down counter by taking the up counter as reference circuit. I repeat, again don't confuse. In the explanation, I can, within this 45 to 60 minutes of time duration, I can focus on only one type of counter. It should be the up counter. So there are some properties applicable for up counter as well as down counter. Of course, the count sequence will be different for up counter and down counter, but there are some properties, those properties are same for both up counter and down counter. So that I don't touch or I don't talk anything about the down counter, because without explanation, if I touch the down counter operation or if I highlighted the related points, unnecessarily it will create the confusions. Okay. Yeah, in asynchronous counters, there are 2 types, ripple counter and mod n counter. Of course, it is basically a ripple counter. If in the middle of the operation, abruptly, if I want to clear the counter or restart it from its initial state by applying some external circuit called strobing circuit, in that case, it cannot produce all possible states. For example, if the given asynchronous counter is giving all possible states, all its maximum possible states, in that case only we can call it as a ripple counter. For example, n is equals to 3. Here n represents number of bits or number of flip-flops. Or number of bits. So possible states with 3 bits or 3 flip-flops, 2 to the power of 3. If that counter is producing all 8 possible states, I can say given is, if it is producing 8 possible states, 000 to 111, 0 to 7 in decimal. In that case, I can call it as 3-bit ripple counter. I will show you the gate questions also. Not only in gate, for electricals, in public sectors also, some questions are found from this area, because it is very simple. Because we are talking about the basic level only here, okay. 3-bit, I can call it as 3-bit ripple counter. 3-bit ripple counter. Again, there are some extra topics, of course, here. We are providing asynchronous circuit of, we are providing what we call clock in asynchronous mode, that's okay. But how they are triggering, or if you apply the external strobe signal, based on that again there is some sub-classification, but I don't touch it here. Yeah, coming to the very basic circuit, before going to the very basic circuit are 3-bit or n-bit or 4-bit asynchronous counter. Yeah, I will start with the 3-bit asynchronous counter. I hope majority of you people who are watching this video may having like some basic idea about flip-flops. If not, you better to understand this. Very simple. I cannot give you the detailed information about it and internal circuit of the clock excitation and types of clocks. I just want to give you some brief idea about the triggering. Then only you can understand the counters operation, right? See, my dear friends, if I take a JK flip-flop, because in asynchronous counters we are using a flip-flop in toggle mode. We are taking the flip-flop in toggle mode. Toggle mode means it can be JK flip-flop, D flip-flop or T flip-flop. I will prove it. But for every clock pulse, output should be toggle. Output should be changed from its previous state called toggle. It can be any type of flip-flop. Let me take I don't know the type of flip-flop and I don't know its interconnections. But this is my expectation. For example, if I give the clock pulse like this, initially this is output. Initially output is 0 or it may be 1, no problem. For every clock, for first clock, if I give the first clock excitation, it should change from, it should change its output from 0 to 1. 0 to 1. If I give the next clock pulse, again it should complement output from 1 to 0 and 0 to 1, like this for every clock excitation. Indeed, it is for every clock edge. Alright, we are using edge triggering type. So just understand, for every clock, output is going to toggle. Toggle means complement of its previous state. That kind of flip-flops we are going to use in asynchronous counter design. Okay, coming to the types of clock excitations. Types of clock excitations. See guys, this triangle represents this triangle inside the flip-flop. This triangle represents the edge. It may be rising edge or falling edge. For example, if you give the clock directly to this, means if you give the clock, this is a TC, clock duration. This is a TC. In this arc, this is a complete clock cycle having 2 half cycles. So if you give this entire clock to this flip-flop will be triggered. Whatever may be the operation, JK flip-flop will, J and K values will decide it. So that I am assuming you know the JK flip-flop truth table. Yes, you see, if I take the JK flip-flop here, J and K are the excitations, Q and Q bar are the output lines. I don't want to waste the time, quickly I am writing the truth table. If JK values are 0, 0, no change, our output is previous state. 0, 1, it is a data transfer state, output 0, 1, 1, 0, output is 1, 0, 1, 1, output is toggle. So for today's class, you just remember this operation, this is enough. I can tell you like that only, okay, because I cannot explain the JK flip-flop operation now, because we need to go for the counters operation, right? If J and K are 1 and 1, for every clock pulse output is going to toggle, but condition is, it will happen in the presence of clock pulse only. It will happen in the presence of clock pulse. Clock pulse must exist for the flip-flop. I am assuming clock is available everywhere. If clock is not available, sir, whatever may be the inputs, output will maintain its previous state. That's it. You remember it temporarily. Right. Coming to this, J and K values are 1 and 1. You take Q and Q bar output lines, and we are going to focus at the output Q only. Right. Now, I am assuming initially output is 1 or 0, no problem. 1 or 0, no problem. If I give the clock at a particular portion of the clock pulse only, the flip-flop will be toggle. Sir, how do you know whether it is toggle or data transfer? You know, this is a truth table. If J and K are 1, 1, output will be toggle. J, K are connected at 1 and 1, so that it will be toggle. But exactly at what time it is going to toggle? Exactly at the falling edge. You see, bubble and edge. This triangle represents the edge triggering type. So that this type of flip-flops only active for the falling edges, because 1 to 0 transition is a negative edge of the clock. Examiner may not provide it in the paper clearly. They will give you only waveforms, and it is the responsibility of the student. You have to understand the type of counter, you should recognize it, and accordingly you should take the arrow marks on the clock. Right? It is very important. So that, sir, if there is no bubble, sir, if there is no bubble, I can call it as rising edge triggered. I can call it as rising edge or positive edge trigger type. Rising edge or positive edge. It means this type of flip-flops, I am assuming this is J and K. As usual, I will take it as 1 and 1. This type of flip-flops will trigger only during 1 to 0 transitions. This is a falling edge trigger and this is a rising edge trigger, or falling edge is also called as negative edge triggered rising edge is also called as positive edge trigger. You please remember this point, then only you can understand the next circuit operation. Okay, right. It is a 3-bit asynchronous counter, 3-bit asynchronous counter. And remember, my dear friends, the output of certain flip-flop which is connected directly to the external clock can be considered as LSB. Once if I write the binary table, you can understand why I should call it as LSB. I am taking it as Q0 now, Q1 and Q2. Remember, J and K are connected, they are fixed at logic 1. That means all the flip-flops are operating in toggle mode, point number 1. Next, I am going to provide the clock here, I am going to provide the clock pulse here, right? And as I told you, this is a LSB bit and this is MSB bit. Remember, while doing the analysis, better you assume initially counter is in clear state. Sir, what is the meaning of clear state, sir? Very simple. We should consider outputs of all the flip-flops are at 0 level. It is a clear state, right? In today only I will explain about the clear and preset combinations if time supports, right? If I give the first clock pulse, what is going to happen? Simple, my dear friends. If the counter or if the flip-flop, I am taking numbers 1, 2 and 3 such that I can easily address them, right? So, if the counter receives falling edge, then only output will be toggle, that's it. Then only output will be toggles, okay? Right, see, Q2, Q1 and Q0. This is a clock and this is the decimal equivalent. That's it. Yeah. Initially, as I told you, no clocks applied. So initial state is 000. If I apply one clock pulse, I am assuming first clock pulse is applied. One clock pulse. What will happen? Output of first flip-flop will be toggle. 0 will be changed to 1. 0 will be changed to 1. Right. So 0, because it is directly getting the clock, but it is the second flip-flop is actually driven by the first flip-flop. What kind of transition has given by the first flip-flop? 0 to 1 transition. So 0 to 1 transition is arrived. So the 0 to 1 transition does not trigger the next flip-flop. Sir, why sir? Why? Because this is a falling edge trigger type flip-flop. 1 to 0 transition only can trigger it. So that no updates at the output of second and third flip-flop. No updates at the output of second and third flip-flops, right? So let me update it. 0, 0, 1. 0, 0, 1 after first clock pulse. Decimal equivalent is 0 and decimal equivalent is 1. Now if I apply one more clock pulse, that means second clock pulse. I can't write here, that is the reason I am writing here. For every clock, first flip-flop as it is receiving the clock directly, it can be toggle. 1 will become 0. 1 to 0 is a falling edge trigger. So that it can trigger the next flip-flop, output of next flip-flop is going to change from 0 to 1. It has been triggered. But 0 to 1 transition, 0 to 1 rising edge, it cannot trigger the third flip-flop. Third flip-flop will maintain the same state as its previous. It will preserve the same binary. So that 0, 1, 0 will be the updated binary state after second clock pulse. 0, 1, 0 and its decimal equivalent is 2. Just for clarity, I'd like to apply one more clock pulse here. I'd like to apply one more clock pulse, that is the clock pulse number 3. If I give one more clock pulse, no doubt, the first flip-flop will keep on toggle 0 to 1. As it is 0 to 1 rising edge, it does not click or trigger or initiate the second flip-flop, it will maintain the same state. It will maintain the same state 1. As there is no update, here also no update. 0, 1, 1. 0, 1, 1. This is after third clock pulse number 3. So I got a point. If I observe carefully, the counter is giving the count of clock pulses. First clock 0, 0, 1, its decimal equivalent is 1. Third clock 3. So I can write after n number of clock pulses, definitely I can reach the full scale value, all ones. So if you think in reverse, for 0, 1, 1, it is actually the sequence obtained for third clock pulse, as it is 1, 1, 1, so it might be a 7th clock pulse. It might be a 7th clock pulse, that's it, 7th clock pulse. So decimal equivalent value is 7. Sir, if I apply 8th clock pulse, what will happen, sir? I don't know. Let me verify it. See, I am taking the dotted lines, guys. 1, dotted lines. 1, dotted lines, and 1. Okay. So this is a sequence at 7th clock pulse. This is a sequence at 7th clock pulse. If I apply 8th clock pulse, at 8th clock pulse, what is going to happen? Very simple logic, very simple. Output of first flip-flop is 1. If I apply 8th clock pulse, what will happen? It will be triggered. That means this 1 will be changed into 0. 1 to 0 is a falling edge, so it can trigger the second flip-flop. Its output is changed from 1 to 0. Similarly, the third. That means, have you seen this 000 or simply 000 sequence? Yes, sir, it was the initial state. So that no need to write the sequence as 000 again. If you give 8th clock pulse, automatically counter will restart. From its initial state. That's it. So what are the number of, or what is the number of states that has given by or producing by this counter? 000 to 111. That is nothing but the modulus number. The number of states given by the counter is nothing but the modulus number. And actually we have some story about this 8. I will talk about it. Just first I will do one thing. I will draw the waveforms at Q0, Q1 and Q2. Then at least it will be completion of at least 0.1% of the concept. With that I can give you so many observations. And each and every observation can give you an idea to solve the problems from the basic level. Okay. So let me take the clock pulse. But I already told you, they don't provide, we have to take the arrow marks. At every falling edge or rising edge, it depends on the type of the flip-flop using in the counter. So at every falling edge, because all the flip-flops are falling edge triggered, so I am taking the arrow mark. So flip-flop will trigger or toggle, simply toggle at every falling edge. This is a clock frequency. I am going to draw the waveform at the output of Q0. You see, my dear friends, for every falling edge of clock, it is going to change from 0 to 1, 1 to 0, 0 to 1, 1 to 0. It's simply toggling, right? So I can put it on the graph. Initially, I took all the outputs are at 0. So I am assuming Q0 is initial at 0. At every falling edge, it will be toggle. That's it. Toggle means complement of previous. So this is a falling edge. It will be toggles. Can you tell me at this edge, it can be toggle? Yes or no? No. At every edge, it is not going to toggle. I did not say at every edge. I said it will toggle at every falling edge. Right? Falling edge means 1 to 0 transition, like this. like this. So again this Q0 is driving the second flip-flop, so that at every falling edge of Q0 the second flip-flop can be toggle, obviously. So that I would like to draw the waveform for the next flip-flop. What is the output of second flip-flop? Second flip-flop output is Q1, okay, right. Initially it is 0. At the falling edge, it can be toggle. Only at every falling edge, that's it. It don't care about the clock. It always follow only the output of first flip-flop because it is driving the second flip-flop. Similarly, second flip-flop is driving the output of third flip-flop. Okay, I can find only one arrow mark. If you take more number of cycles, you can find completely. It is output of Q2. Initially it is at 0, and at falling edge it will be change, and at the next falling edge it can changes. Okay, this is enough to get some basic information. You see, my dear friends, this is a TC. I am going to give you very important information here. What is the output of or output frequency at the Q0, Q1 and Q2? Very simple. With respect to clock, FQ0 is equals to, you see, 2 cycles are completed here. This is a complete cycle. How many cycles are completed with respect to the clock, input clock? 2 cycles has been completed. But within that duration, Q0 could completed only 1 cycle. It have completed only 1 cycle. So that as it has completed only 1 cycle, I can say in this particular time period, frequency of clock is 2 Hz, then frequency of Q0 will be 1 Hz. Frequency is going to divide by 2. Automatically, pulse width will be double. See, if this is a pulse width x, it will be 2 into x, like that. Because frequency and time are inversely proportional. So that, what is a FQ0? F clock frequency. F input frequency, you can write anything, F clock or F input frequency divided by 2, that's it. What will be the FQ1? What will be the FQ1? FQ1 is equals to, you can take you consider the comfortable cycles only, okay, right. You see, with respect to this, see, this is 1 cycle and this is the next cycle. After completion of 2 cycles, it has been completed only 1 cycle, that's it. So, it has been completed only 1 cycle. So that FQ1 is equals to FQ0 divided by 2 or F clock frequency, F clock divided by 4. Then what is the FQ2, sir? You can guess it. FQ2 is equals to F clock frequency divided by, I will write it in terms of FQ1, okay. First, FQ1 divided by 2, that's okay, or this is important. FQ2 is a overall output of the circuit. FQ2 will be equals to, with respect to the clock, can you guess? F clock frequency or input frequency divided by 8. I already told you, here we have some story about the 8. What is that 8? 8 is a modulus number. 8 is a modulus number of the circuit. How many possible states are available here? Number of states. Number of states. Number of states are equals to 8. Sir, 7s are no. 7 is the highest magnitude. 0 is also a state. Initially, all zeros is also one state. So, zeros to all ones. Total modulus number is 8. 8 states, that is the reason actually I can say modulus number of this counter is 8. What exactly the meaning of modulus number? Very simple. The number of states producing by the counter in its sequence, in its count sequence, that's it. So here I can write the formula for that. For this particular counter, 1 second. Yeah, for this particular counter, what is a modulus number? Modulus number is equals to 2 to the power of n for n bit asynchronous counter. This is a formula for n bit asynchronous counter. That means here what is the n value? Simply I am writing m modulus number. What is the n value? 3, and 2 to the power of 3, 8 is a modulus number. In any n bit asynchronous counter, you remember output frequency is equals to, of course this formula is valid for asynchronous and synchronous also, but I am talking about asynchronous, I don't touch anything about the synchronous case. Output frequency is always equals to input or clock frequency divided by modulus number. You remember this point. This is very important. And from this operation, modulus number is 8, you can say that m is equals to 8 here. And what is the maximum count value? Maximum count value is equals to 2 to the power of n minus 1. N is equals to 3, 3-bit counter. So the maximum count value is equals to 7, 111. That is the reason here you can see the highest value or full scale value as 7. And this is one of the important formula most of the time, but it is a basic, very basic level questions without any logics. If you want to find, of course in recent gate papers also you can find this kind of questions, but you should understand the type of circuit. Compulsory it should be edge triggering. Of course, if it is not a falling edge, then it will becomes up counter, but that story is different. There are two different ways to represent or draw the circuit for up counter and down counter, also having two different ways. But don't worry, I'm talking about up counter and 3-bit, that's it, or n-bit asynchronous type up counter. You remember only these points, right? Next point, this is also called as a ripple counter. Given is a 3-bit ripple counter. Ripple counter, 3-bit ripple counter. If the given asynchronous counter is giving all its possible states, what are the possibilities? 2 power 3, 8. It is giving 8 as its modulus number. In that case, I can call it as 3-bit ripple counter. Remember the point. For example, sir, if it is having 3 bits, sir, but it is giving only 5 states, 0 to 4, 5 states. Sir, can I call it as ripple counter? No. You should not call it as ripple counter. You should call it as mod 5 counter. We should call it as mod 5 counter. Here, there is no limitation for the sequence. Sir, how can you restrict it? Yes, I can do it by connecting external NAND gate or some logic gates. Not only NAND gate, basic level NAND gate, I can do it with XOR gate, XNOR gate, some other logic gates also. That is called as strobing circuit. By connecting external strobing circuit, I can clear the operation in the middle of its own sequence. Right? In that way, I can develop or I can generate modulus counter. Right? So, generally the relation between modulus number and the number of flip-flops should be like this. M should be less than or equals to, while designing the mod 10 counter, I will let you know this. But because first I should explain the mod 10 counter, then I will talk about the relation, why I should use 4, you need 4 flip-flops for mod 10 counter, why I should use 4 flip-flops, and why can't we get by using 3 flip-flops, right? And the formula actually, I wrote m less than or equals to 2 power n, but Okay, first after that, after explanation, I will give you. That is the correct place for that formula. Right. So this is a basic information about the n bit or 3-bit asynchronous counter. You can find the questions like this. For example, for the given counter, input frequency so and so, 8 kilohertz assume. What is the output frequency? Output frequency means that is the frequency at Q2 here. Frequency at this point. The output frequency at this point is equals to input frequency by its modulus number. So first you should find the modulus number. As there is no external circuit, we can directly use the direct formula as it is a 3-bit asynchronous counter, 2 power 3, modulus number is 8. So output frequency equals to input frequency by, I think I have given example 8 kilohertz, output will be 1 kilohertz, right? 8 kilohertz by 8, like that you can solve. But questions are not that much of easy. There is some logic in each and every question, but I am just giving you an idea only how they can design the circuit and give you the problems. Okay. And you see, you take 1 second. Yeah, no problem. I can add one circuit here and I can add one extra block here. Yes. It should be one more flip-flop. Should connect like this, Q and Q bar. Okay. Here I am going to give the clock. And as usual, I am assuming J and K are connected at logic 1. Before explaining this circuit, I would like to tell you one important point about the clear and preset. This is called as control signal. This is called as control signal. See, let me take one flip-flop. I don't give you both clear and both clear and preset. I'd like to give you only some information about clear because I want it. It might be rising edge or falling edge, no matter. It can be JK, TD, whatever, SR flip-flop or maybe XY flip-flop, AB flip-flop, whatever. If it is a JK flip-flop especially, you know what is the output based on the input. If it is SR flip-flop or 0, 0, previous state, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, not allowed. Or if it is a JK flip-flop, same as SR except last 1, 1 case, output is toggle. If it is T flip-flop, only we will have T. If T is 0, output is previous. If T is 1, output is equals to previous. Sorry, complement of previous. Qn plus 1 is equals to Qn bar. Like that, we know everything. Just we can find the output based on inputs. That's okay. But remember, if you find a signal like this is called as clear. There is another possibility. Of course, it is a preset. Compulsory, it requires for the student who are studying the down counters, but now we don't have that much of time. We are studying the up counter only in this session, right? Basic level of up counter. Yeah, see, if this is enabled, what type of clear is given? It may be active low also, no problem. But it is, active high also, no problem, but it is active low. Given is a active low enable type. Active low enable type clear. If it is connected to logic 1, nothing will happen. The system will not consider it. But if it is connected to 0, if you give it to 0, clear will be activated. You remember that output will be clear. Output means no second thought. Don't confuse. By default, Q. If Q 0, don't worry about Q bar. Automatically Q bar is complement of Q. Okay, right? So you always focus at Q only is output, Q is output, right? If clear is enabled, Q will be cleared. Clear enabled, it will be cleared. Clear means if some data is available in the counter 10, 10, 10, once if you enable clear terminals of all the flip-flops in the counter, the total sequence will become zeros. So that is the use of clear terminal. So I don't give you the complicated information, a very simple information. See what I am going to do now. I took one NAND gate here. I am assuming delay is 0. Delay based operation is different story. I have written that in the introduction page. Steps. Delay, if I talk about delay, I should talk about TC and FC maximum. Okay. I am just connecting the two input NAND gate, one input of NAND gate to the Q3, this is Q0, Q1, Q2 and Q3. This is MSB, clock is connected here, this is LSB, okay, right. And one terminal to the Q1. Then I'd like to consider the output of this NAND gate. I am assuming these all are clear terminals. All are clear terminals. And this output is connecting to the clear terminal. Now you focus at this node, focus at this node. If this node is logic 1, what will happen? Nothing will happen, because no flip-flop will be activated for this one, because all are active low enable type clear terminals. They are having active low enable. If this is 0, then all flip-flops can be cleared immediately. At any instant of time, I can bring them into clear state by enabling this line. But it is not in my hand. It is actually driving by one external combinational circuit, and here which is consisting of only one NAND gate. This is a NAND gate, right? So if output is 1, no effect. On the counter or on the counter output. But if it is 0, all flip-flops will be cleared to zeros. All the flip-flops will clear to zeros. So this is Q3, Q2, Q1 and Q0. This is a NAND gate. Initially sequence is 0, 0, 0, 0. What is output of NAND gate? 0 and anything 0, 0 bar 1. No effect. No effect. I can keep on give the clock pulses here. 0 clock. No clock is given so far. 0, 0 after giving the first clock pulse. 0, 0, 0, 1. Still it is 0. I just keep on giving the clock pulses. If I reach 1, 0, 0, 1, just assume, it is a 9th clock pulse. 9th clock pulse. Sir, this is 1, sir. This is 0. 0 and anything 0, 0 bar 1, no effect, right? If I give the 10th clock pulse, what will come? 1, 0, 1, 0, but instantly within 0 time delay under ideal conditions. Practically it is having some story, but ideal conditions, no time delay. If you give 1, 0, 1, 0, and immediately what will happen? See, this is 1 and this is also 1, 1.1, 1 and 1 bar 0. You cannot see this state on the display unit. You cannot see that because just immediately if the edge is arrived, within no time. It will not stay. This 1010 is not able to stay in the display unit till to receive next edge. Within the edge itself, once if you give the trigger clock, within the edge itself, the outputs of flip-flops are going to clear. So how many stable states are available? 0 to 9 are the stable states. So for this circuit, zero to 9 are the stable states. Total 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 can be displayed by this counter, so that given is a mod 10 counter. 0 to 9 total 10 states, given is mod 10 counter. So if I want to design mod 10 counter, number of flip-flops requires. Sir, can I do it with 3? Not possible, because this is a formula. M is less than or equals to 2 to the power of n. You remember this formula where M represents modulus number, n represents number of flip-flops. You know, you better, you write it. I wrote in introduction page, M means I will use M for modulus number, n for number of bits or number of flip-flops, both are same, because one flip-flop is a 1-bit storage element. Okay. So if it is 3, 2 power 3, 8, but I want 10, 10 less than or equals to 8, not satisfying. It should be 4 compulsory, so that it can satisfy. But if it is 4, 2 power 4, 16 will come. Without any external circuit, it is a 4-bit ripple counter. Remember, without any external circuit, it is a 4-bit ripple counter. Because if without this, it is going to produce 0000 to 1111. Total 16 states, 2 power 4, 2 power n. That is the modulus number of that counter. But here, modulus number is limited by 10 only. Why? We are limiting it by using external circuit. Like that, you can fix the modulus number based on external circuit, but we need to satisfy the number of bits from this particular formula also, right? So I have decided to continue the session till to give some example problems also. But see, I would like to continue the same session, same topic in the next session. I will continue the same topic in the next session. Actually, the expected topic, next topic is counters in cascading. If I connect more than one counters in cascading, and the two similar and known counters. Known counters are n-bit asynchronous counters. What is the resultant modulus number? And I need another 40 minutes to touch at least any single question from this topic, right? So please, if it depends on your comments, yes, please try to make some comments based on that. If you are interested and you are able to follow it, and if you are interestingly doing this, I can definitely come up with some more huge number of numericals. Simple topic is enough. It is even, it is 11, not 0.1% of the entire counters, but even just 0.1% of this counter topic also, we can create hundreds of questions. We can create the questions, but we better to solve the previous year gate questions, then we can understand how they are framing the questions. In that way, we also can create the questions, right? So as a time is already 8, that is the reason I am going to stop the session now.
My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work. because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you.